As the title indicates, it's the 150th anniversary of 150th birthday of Ludwig Boltzmann, the great Viennese genius about whom you'll find out a lot more in an hour's time. We all have our personal heroes, like Einstein and Feynman and, well, Boltzmann. Some of us have more than one, but certainly Ludwig Boltzmann is one of the personal heroes of my friend and colleague, Dr. Norm Frankel, who is the representative of statistical mechanics in this school. And, well, when he came around to who's going to give the lecture in honor of this particular anniversary, of course, there was an obvious answer to that. Dr. Frankel is one of the, for those of you who don't know him, is one of the most popular and interesting lecturers in the school, and for those of you who don't know him, you'll find out soon why. So it gives me great pleasure to introduce him to give this July lecture, the subtitle of which is The Arrow of Time. Dr. Frankel.
It's always hard to follow an introduction like that. You think you should take your clothes off, or better than that, ask the audience to take all your clothes off or something. I usually do that to the first-year students, and nowadays some of them do. And I'm sorry that I asked them. Okay, the title of today's, I was going to use the word sesquicentennial because someone told me that means 150, but I didn't use it because I didn't know that. But Boltzmann, Ludwig Boltzmann was born 150 years ago, 1844, and he is essentially known as, rightly so, the father of statistical mechanics. And this word statistical mechanics sounds, I don't use these things. Can anyone hear? I used this in first year once, and I had to pay the earlobe bill for two of the kids in the back row that claimed that I burst their eardrums or something like that. So, statistical mechanics deals with statistics and mechanics, and so it's the kind of theory that is applied to large ensembles of large numbers of molecules. So I'm going to start out really slowly and tell you, and I hope I don't bore you, a little bit about who Boltzmann was, a little bit about what statistical mechanics is, and a little bit of the consequences of that for our understanding of time. Now, when I started to think about what I would say about time, time's arrow, by the way, means the unidirectional nature of time. That is to say, very few of you in this room believe that in a certain period of time you'll reach a certain age, and then all of a sudden things will simply be reversible, and you'll just get younger and younger and younger. Jewish fraternity or culture, 120 is the full length, 60 is halfway, and then you count back from 60. So I tell all my Jewish mates that they're really only getting to 59 and 58. Time really isn't unidirectional, but most of you know, and I don't want to hurt your feelings, that you're going to carpet, snuff it, die, piss off the planet Earth, never see it again. And it's going to happen in a unit called your lifetime, and it only goes in one direction. But you're going to see in principle that the laws of physics allow for that to not happen, but for some reason it does happen, and that was one of the things that consumed Boltzmann's life and led eventually to great fits of depression, and on his 62nd birthday he stood on a chair and hung himself. So I want you to know the consequences of studying statistical mechanics in the arrow of time have certain mortality problems. He handed the scepter of this problem on to a brilliant young physicist named Paul Ehrenfest, who took up the scepter of why the laws of physics seem to be reversible, but in nature they aren't. I'll say much more about the things I'm talking about as I go on. My normal idea in lecturing is to just dump everything I know randomly and then sort through it and hope in the very end you thought, I really think he sort of made sense, but what the hell did he mean? And if you can do that for 15 lectures, you can get paid and you can be a university lecturer, and maybe no one will ask you a question. So it'll all hold together, I hope, but my way of doing it is just to let it all hang out. Sorry. My wife said, don't come out from the podium. I have three shirts so I can take two off before the lecture is over. I've never lectured in here in all my 31 years at Melbourne University. I should say that the arrow of time is very personal because as I was driving in this morning, I was thinking about being old and what I would talk to you about psychological time and biological time after I established with you a little bit about what Boltzmann did to give us the meaning of time in physical reality, that is to say in the natural sciences. And I remembered, I don't know why, that the first day I arrived in Australia was on April 25th, 1963. And there were no jets I mustn't do this. It's all going to. There was no jets to Melbourne, as you probably know. You flew to Sydney, and then you got on the Fokker Friendships. I think I pronounced that correctly. And you rolled up the propellers really quickly, and you ran in, and then went zoom, and you flew from Sydney to Melbourne and landed in Essendon. And the green bus that took me in was driven by a Yugoslavian man who I still stay in contact with. The cab I took was driven by an Italian. And when I got to the Melbourne University Physics Department, which is called the School of Natural Philosophy, it had two things on the wall. One said, "Don't go to Spotless, they lose things." And the other said, "If you're a Yankee, turn around and go back home." It really did. And it was about the Cuban War. It said, "If you're a Yankee, go home." So I just thought my arrow of time didn't really fulfill the symbolic omen that was on those walls, which sort of didn't do this. So I'm still moving into the carp direction. My wife says I'm here for the term of my natural life, which is, as you can tell, 31 years ago. Okay, so to start with, I want to tell you what Boltzmann thought a little bit about, and as I go along, I'm going to interweave some books. I happen to have 2,003 of each one outside, and prepared to let them go for a trip to Tasmania or whatever you have in mind. Okay, one of the best books on this recently written, and I'll put it up, it's called The Arrow of Time. I didn't want to steal that title, so I call it Time's Arrow. And it starts with Boltzmann, but it has all the concepts of time as they appear in the physical world. That's to say, biological sciences, biological clocks, chemical reactions, and physics. But I'm warned by Boltzmann that I would love to do some things like talk about psychological time, like things that Jürgen Freud talked about. Turns out Einstein was very interested in time, as you probably know, and he wedded it with space. I think Dr. Jamison gave you a really beautiful talk on how you're really, as you already know anyway, married in a four-dimensional space-time, and space and time go together. And it turns out that one of Einstein's all-time best friends was Freud. And Freud was always angry with Einstein because Einstein wouldn't nominate him for a Nobel Prize. And when Einstein was finally asked by Freud at one dinner why, he said, "You're a wonderfully intelligent, incredibly creative man, but you talk a lot of nonsense." So I don't know if that's true and if there are any Freudian or Jungists out there. I didn't say that. They tell you the sensitivity scientists have to psychological matters. But time bothers you all because we only have a certain amount of it. I could probably use that 8 minutes of it anyway. Anyway, I would like to talk to you about the metaphysics of time because it really fascinates me. When I went away to college in the States, in the university, I had never read any of these things about philosophy. My high school had things about how to farm and we passed the physics exam by memorizing 325 questions, of which 45 would be on the state exam, and if you could memorize all 350, you got past it, so I had a good memory. But nowadays, I learned a lot about all the psychological and metaphysical aspects of space and time. To be honest, we don't have a clue what space is. If you had to try to tell your daughter, I have a 4-year-old daughter, she said, "What are you going to talk about today?" And I said, "I'm going to talk about time." And she said, "You mean when you're coming home for dinner?" And I thought that was a good answer. And I said, "I'm going to talk a little bit about space." She didn't have any idea in any literal way what I was talking about. We really don't understand these concepts, and we talk about them in great detail, and we call them X and Y and Z and T, but it's really a great mystery. And I would like to talk to you about some of the metaphysical aspects, but this is to celebrate and commemorate Boltzmann's 150th birthday. I hope I lead you in a serious way with an understanding of why he was literally one of the great minds of the 19th and 20th century, and will certainly win a Nobel Prize winner had he not taken the other exit. Boltzmann got metaphysics, a migraine of the human mind. The most ordinary things are to philosophy a source of insoluble puzzles, he remarked. With infinite ingenuity, it constructs the concept of space or time, and then finds it absolutely impossible that there be object in space and time at all, particularly the person thinking about whether anything is in space and time. This is madness. If all this logic seems to be as if somebody for the purpose of a mountain bike were to put on a garment with so many long folds that his feet became constantly entangled with them, and would fall as soon as he took the first steps into the plains. The source of this kind of logic lies in excessive confidence in the so-called laws of thought. Boltzmann criticized several philosophers and is known to have hated Hegel, Schopenhauer, and Kant. So I don't want to say that he was right, but I would love to go into certain aspects of this with you. And there have been a lot of beautiful books written on that, and I just want to tell you that I won't do it because if Boltzmann is listening, he may be fixing a chair in my kitchen, and because I will come home slightly inebriated, there may be something hanging from it, and I may do myself an injury. So the question I want to ask you to start off thinking like Boltzmann is, when you get in bed at night, that's got to be sexual to start with, it has to be, I have this problem. When you get in bed at night and you're very cold and your partner is very warm, why is it that you don't get, when you snuggle up, you don't get colder and your partner gets hotter? Does that really happen to you in your personal life? For example, when you put a cold block next to a hot block, why doesn't the cold block get colder and the hot block get hotter? You say, well, that's impossible. Why is it impossible? Well, it's impossible because it doesn't happen. Well, why doesn't it happen? Well, it doesn't happen because most people say because energy is violated. And I say that's not true. If I take a cold body, put it next to a hot body, I hope I have you thinking something non-physical at present. So I have a hot body and a cold body, and I put them together. The amount of energy that I transfer from the hot body to the cold body to make them equal in temperature, I could do it the other way and transfer the same amount of energy from the cold body to the hot body. I wouldn't be violating conservation of energy. As long as one body lost the amount of energy that the other body gained, I would be conserving energy. But that process doesn't occur. Why doesn't it occur? Or if you have two bodies in equilibrium at the same temperature, why doesn't one of them suddenly get much colder? Like when one day when you're in real need of a cold drink, you put your beer or your wine in the refrigerator, why doesn't it get infinitely hotter while some body of water in the Sahara or some oasis with some camels drinking instantly freezes over? Poor damn camel with his tongue in his water. Really scared camel maker. It can happen. Or another question, why don't all the molecules in this room suddenly find themselves in one half of this room? Some of you haven't laughed, so I know that half is going to happen to you. So I want more laughter from some of you, or molecules are going to decrease rapidly. They're all moving around, you would say. Why don't you find that all of a sudden, some instant in time, that all the molecules in the room, well, this, they don't wind up on, smiles, on this side of the room. They smile over here. And there's no molecules over here, so there's a lot of carpet dying going on. There's a lot of death. Why doesn't that happen? There's nothing to prevent that distribution or that particular situation from occurring. I'm going to go a little bit more quantitative in a minute. Why don't all the molecules in this particular room decide to take a particular antagonistic view to one of you? And instead of moving around in whatever way they're moving around, like incredibly rapidly moving bees, they park themselves right under your posterior and impart all their energy to you. It's an easy calculation to work out that if some of you weigh 50 kilograms, I don't know anybody that little. If anybody of you weigh 50 kilograms, it's easy to work out from the room temperature in this room and how many molecules there are, that you would be lifted up about 11 and a half feet. So why, if I watch you, now all the molecules stop moving, and as we're gasping for air, one of you is spontaneously going through the roof. Why don't the molecules suddenly take a configuration where all their energy, they have a lot of them, not each one doesn't have a lot, but there's a lot of them, and suddenly have one particular configuration that happens to be ejecting one of you out of your seat. Why don't those things happen? Say, well, they can't happen. Well, why don't they happen? Well, these are the kind of questions that were... Here it is. Sorry, you're right. I never used this room. Graham used to use this room all the time because he got all the big classes. You can see why they didn't give me big classes. They gave me very little classes. Newton once gave a lecture with no one in the room because he said he was paid to do it. He had one student. The student didn't come, and Newton gave the whole lecture because he said that he was paid to do it. That's the truth. I think it was probably his best lecture. I would have loved to have been a fly on the wall with this brilliant genius thing. And now we take the Kepler laws of motion, which no one understands, and I will tell you it goes like wonderful. Okay. So let's do a simple calculation. Let's take, for example, let's take 10 particles. And so they can be distinguishable. They're numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or red, green, blue, or whatever. They're distinguishable. And let's put these 10 in a box, which is divided into 2 parts. Part 1, called A. Part B, called L. You thought I was going to say B. Part B, sorry, in this side. And let me work out what the probability is of finding these 10 molecules in various configurations, because that's what I'm talking about when I talk about what's the type of situation these 10 particles, and let's work out what the probabilities are. So we're using a new word. You probably all know it, but the probabilities of various configurations occurring. What do I mean by various configurations? Well, suppose that I have, this is box A. These are my containers. Let me make it chart, which would be better. Like all my lectures, they're unprepared, so they could turn out to be a disaster, or it could turn out to be a disaster. So let's call this A and B, and this P for probability, or total number of combinations. Let's use C for combinations. Different ways I can form a configuration. You'll see what I mean as I go along. Suppose I want no particles in A and all 10 in B. And I want to work out what is the probability if I have 10 molecules that they will be none in one half of the box and 10 in the other. That's the kind of situation we talked about with all of them here, and none here, but I have a large number of molecules. Let's start with 10. And I won't bore you with it, but does anybody know what the binomial distribution is, or you know what of course you do. So this is the thing for those of you that know. This is called, okay, 10C2. I'm going to take these things in different ways. But another way is to do it this way. It would be 10 factorial over A factorial times 10 minus B factorial. I write it like that, where A is the number of particles that are in box A, and B is the number of particles that are in box B. Maybe you've all done this before. You all know the binomial coefficient. So I should have worked this out for you, but I was having a nice dinner with Tony and Graham, and I didn't do it, and I'm no good with numbers. The number of ways of doing that is 1. You would put none in one part, you would put none in one side and 10 in the other. There's only one way to do that. Okay. And suppose you had 1 here and 9 here. And the way of doing that is 10 different ways. Putting 1 particle here and 9 here, and then another particle here and 9 other ones. I mean, remember, they're all distinguishable. And the number of ways of putting 2 particles in 8, it's going to get hairy. 10, 9, what is it? 20. I have to do this. 10 factorial over 2 factorial times 8 factorial. I'm sorry. See how a really good physicist works with no intelligence whatsoever. I can't have done that right, huh? What have I done wrong? I told you to mess up. Yeah, I am, but what am I? Yeah, that's right. 8 times. You're right. That's absolutely. Come. They don't know absolutely nothing. And if they do, they have to get out. Or take their clothes off. All right, I'm hoping. Okay. I'm just not good at this. So.
Norm, if you give them lip, they won't help you with the next number.
Okay, I'll be good. 45. All right, 3 and 7. You could go for it. What is it? 10, 9, 8, 3, 2. Did you buy 120? Would you say it was 120? Yeah, I like that person. 4 and 6. I should have worked it out. I should have prepared it, but I'm no good if I prepare it, because then it's not spontaneous, and I probably will leave all my clothes on, and it'd be no fun. Okay, 4 times 3 times 2 times 1. You know factorials? Are there any people that don't know what a factorial is? You have a number factorial. You just take it and you multiply the number times the number minus 1 times the number minus 2 times the number minus 3 to get down to 1. So if you have 10 factorial, you're writing it as 10 times 9 times 8 times 7 times 6 times. I can use the whole extra. You never know who the hell holds me. 10 times 9 times 4. Okay? Thanks, Graham. He knows me. Yeah, if I don't say this, guy's in real trouble. And then it's 5 times 5, 5 and 5. And what are the number of combinations there? I think it's 250 something from memory. 10, 9, 8, 7, 6, divided by 5, 4, 3, 2, 1. So 8, 3, 2, 36 times 7, 252. And then I won't do the others for you because you can see their symmetry. Can you see that? That if it's now 6, 5, 6, 4, 7, 3, 8, 2, 9, 1, 0, it'll just be these same numbers again, but the combination will occur for the other side of the box more than this side. So what I want to show you is that just with 10 particles sitting in a box, the probability that there's an even number of particles at either side of the box is the largest. By probability, I could work it out for you. The total number of combinations, if I write the other ones out, 6, 4, 7, 3, 8, 2, 9, 1, 10, 0, and you add them all up, as you'll probably know, the total number of combinations is 2 to the n. And here I have 10, so 2 to the n is 1024. I know that because I use it in Cat's Lotto numbers. Never works. Okay. So if you wanted the probability, you would take this thing here, call this C, the number of combinations. You take C and divide it by 10 to the 10, and you could form a probability. So it's 1 part in 1,024 is the probability that they'd all be on one side. And it's 10 on 1024 that there'd be 1 on one side and 9 on the other. Either way, 1, 9, or 9, 1. So it's preferred, just statistically, more probable that the number of possible combinations are 252. Now you might argue that 252 and 210 ain't that damn different. And they ain't that much different than 120. So it ought to be possible. Well, what happens now if n goes to infinity? Or better yet, n goes to the characteristic number of molecules that you'd have in 1 gram molecular weight. And there's a lot more than 1 gram molecular weight in this room of air. I'm not going to count the gram molecular weight of bodies. The number of molecules in this room would be 6 times 10 to the 23rd, Avogadro's number, if there was 1 gram molecular weight of air, but there's much more. So what happens now when I'm not playing with 10, I'm playing with 6 times 10 to the 23rd molecules. What's the overwhelming probability? So you can relax and go home and hold your breath. The overwhelming probability is going to be, when you do this 0 over 6 times 10 to the 23rd, 1 over 6 times 10 to the 10, so forth. Well, it won't be those numbers. They'll be much smaller. The probability is that you're going to have overwhelming number of particles with n on 2 on one side and n on 2, an overwhelming number of combinations for n on 2 on each side. And so you can relax. It's overwhelmingly huge. I could work the numbers out for you if I had worked them out, because I used to be able to do these things when I was young without any preparation, but now I seem to muck up a lot. But you get the feeling I could work it out. You could work it out. And then you could use an approximation called Stirling's, because you might say, well, what do you do for n factorial when it's very, very large? Then you can use a thing called Stirling's approximation. You can actually use some math. And you can prove not only is the largest possibility overwhelmingly n on 2 on each side of the box a uniform distribution, but that the probability is enormously peaked. In other words, if I was to plot the probability, that's the total number of combinations divided by 2 to the n, plot that versus the particular configuration, I would find as n got bigger and bigger and bigger that the probability distribution looks something like this, a bell-shaped type of curve, but as n got bigger and bigger and bigger, that bell-shaped curve looked more and more like a spike, overwhelmingly peaked at the configuration n on 2, n on 2. Shape of this curve is called a bell-shaped curve, or a Gaussian. You ever heard of that word? Gaussians in statistics? And these sort of distributions represent the distribution of a particle or a variable distributed randomly. I don't know what you know. You probably know instantly. You're also giving this talk. I should be up there. And 10 to the 23rd of you should be talking. Bell-shaped Gaussians represent random processes. So when you work the mathematics of all this out, and this is what was going on in the 19th century, well, the 18th century with Gauss. This is Gauss for Gauss, the great mathematician and physicist, that represents random process. So the distribution of the molecules in this room are following some kind of random process, and because there's so damn many of them, you can be safe that you'll breathe for whatever arrow of time that you have. Okay. What does this have to do with the arrow of time? What does this have to do with Boltzmann? Well, as these concepts of probability were being emerged, they were also becoming linked with the concepts in physical world. These are mathematical concepts, this probability of how the particles in this room would be distributed, and the random distribution gives you the most preferred distribution of half on either side. What does this have to do with physics? What does this have to do with a cold block and a hot block that I started with? This lecture is supposed to be coherent. Incomprehensible, but coherent. So I should at least be consistent with all the topics I talk about. So in order to make this concept, we can bring in one of the great 18th century, 19th century physicists named Clausius, who's responsible for the introduction of the concept of entropy. Now, when I was an undergraduate, I was told, you know, certain things you weren't supposed to do with members of the opposite sex or with tiny turtles. And one thing that you should be scared about when you went to the university was entropy, because you would never understand it. And I remember thinking, if that's the most ununderstandable thing there is, then I want to understand it. And so I failed the course, like everybody else did. Spent my whole life trying to figure out what the first lecturer who taught me this stuff was. Seems like a really hairy concept. But nowadays we understand it really well, and I'll bring him in a minute, thanks to our mate, Ludwig Boltzmann. And there are others too, like Clerk Maxwell, the founder of the Maxwell theory of electromagnetism, and also Albert Einstein. I mean, Al was everywhere. There was no branch of physics that he didn't touch, illuminate, and you could have given him a Nobel Prize for it. So Big Al has to enter it. But right now it's Big Ludwig we're into. So first following on Clausius, and then we'll come to Ludwig. And Clausius got the idea of playing around with entropy. Now, some of you know that if you have a system, this is some system, and it's in some state, whatever it is, it's got some temperature and some volume, and call that initial state 1. And then you do something to this system. You breathe on it, you sit on it, you know, you do something to it, and you change its temperature and its volume, so finally it has some state called 2 at a different temperature, different volume. You compress it, you heat it up, you remove temperature from it, you expand it, you do something to it. Then a concept called entropy, which really came from Carnot engines, as most of you know, Carnot engines, and the French engineer Carnot, which was classified really by Clausius into a physical kind of law, that the change in a quantity called entropy, S is entropy. I don't know why it's entropy. It should be E, but it's not, it's S. Kids ask me, why do they call entropy S? And I said, why don't you worry about what it means? And I said, I don't understand what it means, so the decent question is, why the hell do they call it S? Okay. So I agree with that. I don't know why they call it S, but I know what it means, so I'm probably stupid. But the change in entropy and going from some initial state to a final state, I'm cheating. It's some integral, and I really shouldn't pull the T out. But for the process I'm about to use, it'll be all right to do it, because I'm going to do something in which when I go from 1 to 2, I don't change the temperature of the system, called an isothermal process. So I've cheated on this formula, but you can just trust me. I look like someone you can trust. Not with your daughter, but with entropy. It's that. Really, whole life has been like that. Walk into a room and they say, as a man, you can look after my entropy, but don't touch the cat. Okay. Very unhappy situation. I have 5 wives, all called entropy. Delta S 1, 2 equals delta Q 1, 2, 1 T. I shouldn't pull the Q out, but I'm doing a process which 1 and 2 are both held at the same temperature. This is what we would calculate, and there are ways to do that from thermodynamics. I just learned how to spell it. Some of the people in the room are students, ex-students of mine, and they know that my handwriting is terrible and I'm writing big, so they're going to say, you write big for the audience, and a free lunch, so you never wrote big for me. That's one of the things they say this afternoon. And you never could spell thermodynamics. But I did, I spelled it wrong. Thermodynamics. Okay, this is the thermodynamic result. Thanks to Clausius, we get the idea that the change of energy, now we're going to go molecular. This has got nothing to do with molecules. Somehow you have your system. Here's your system. Here it is. Normally my system looks like Australia. I don't know why. Today it looks like a peanut. But this is my system, some container of something, and I'm going to hold the temperature constant, and I'm either going to transfer some heat energy, I'm going to have a change in the heat energy. I'm going to heat it up, transfer some heat either to the system or from it, and the change of entropy is going to be delta Q1, 2. That's the change in taking it from state 1 with some heat content to another one. You shouldn't talk about heat content, you should talk about the change in heat, but let me be sloppy. You can trust a person like me to be sloppy. Okay, let's say the change of heat content is delta 1Q, and it may be positive or negative. If it's positive, I've transferred heat energy to the system and going from 1 to 2 at temperature T, and if it's negative, I've taken some heat from it. Okay, thanks to Clausius and Boltzmann now. So at last we have Boltzmann in at 8:34. Because I talk a lot and I wandered around a lot and I wasn't sure what I was going to say, and now I see the people in the room that I like and those I don't like. those whose clothes I'm mentally taking off know them. This is K times the log of W2 over W1. Thanks to Clausius with this, Boltzmann actually took it to here on a molecular basis. Back to these things, you can talk about those C's as W's now. Combinations or probabilities that the system will have a certain molecular configuration. So these W's are now like these C's, and this delta S12 on a microscopic level is K, I'll say what K in a moment, times the logarithm. This is to the base E, but you can have it to the base 10. It doesn't matter if that's a log or log to E or log to 10. W is the probability that the system will be in state 2. All the molecules will be in a configuration where the temperature hasn't changed, but you've passed some heat to it. And W1 is the probability that the system will be in state 1 before you took heat into it or out of it at the same temperature T as it was before. So these W's are like your C's. And this quantity here, this is Boltzmann. This constant is Boltzmann's constant. So what I'm trying to say is that Boltzmann, after much thinking, Newton was wonderful. A very old lady asked Newton when he was a very old man how it was that he came to discover the laws of gravity and to explain Kepler's law and essentially found modern science. He said, literally, after a long period of time of thinking, he said, Madam, he said, it came to me after an inordinate amount of thinking. So you get the idea that Newton wakes up, black plague, you know, it's all black plague time, he rushes down to his mother's place and he doesn't eat the apple, he lets it hit him on the head. You know, the black plague's killing people in Europe. He wakes up, oh my God, the laws of nature, and he writes it all down. It doesn't happen like that. It didn't happen with Boltzmann like that. It took a long time, almost a whole century, certainly a half a century, and a lot of names like Helmholtz and Kelvin that I'm not putting in here. But linking this is thermodynamics, things that you observe in the laboratory by changing heat content, heating things up, making them hot, keeping the temperature the same, and then relating these things down in some mystical way to the probability that the molecules are in a particular configuration corresponding to having heat added to it or heat taken away from it. This is the probability that the system's in its initial configuration, loose. Don't worry about it in a technical way. I don't have a lot of time. W2 is the probability that it's in the second state when heat's been added to it or taken away. So this allows me to calculate it thermodynamically. I can actually take heat in or out of the system at a constant temperature, and thanks to Boltzmann, this is his constant. Pretty good. One of the things, if you're a physicist, you can hope for is that you live long enough to get superannuated, win the Nobel Prize, or have a constant named after you. Or that your children talk to you. But that has something to do with being a physicist. My 31-year-old daughter is starting to talk to me again. I'm realizing what it meant when she didn't. She's talking about money, things like that. They come back. Do you have any? I know I look too young to have a 31-year-old daughter. I have a 47-year-old son. I'm going to talk about that. Like that. Okay, delta Q1 on T is how you do it thermodynamically, and this is Boltzmann saying this is what it means on a molecular basis. Without worrying about how he arrived at this, let's just play with this thing. And let me come to my old formula. Let me do something about that weird thing about the molecules coming and hitting you on the bum and putting you into a weird configuration, or something getting hotter rather than colder when it's in contact. Let me do a different calculation to relate to the things I started to talk to you about. Let me take a container full of a lot of water. A beaker, a glass of a lot of water at 0 degrees centigrade, just at the freezing point of water. And I want to calculate what's the probability that 1 gram of that water will spontaneously nucleate into 1 gram of ice. I mean, very few of you sit there with a glass of water, stare at it, and find that it suddenly becomes hard ice in front of you. It doesn't really happen. If you put 1 gram of ice into a beaker of water at 0 degrees centigrade, the ice will melt. It will become part of the water at 0 degrees. I want to do the other thing. I would like to do something spectacular and have the whole damn thing freeze. Because most of you, I'm dying out here, most of you are yawning and picking your nose and never going to take your clothes off. Well, I like the whole room to be filled up with water and have it spontaneously freeze. But every one of you that aren't pleasantly enjoying this talk, embedded in sort of one of Dante's Inferno layers, of ice. But I won't do that because I'm not as vindictive as that. But I think that if I lecture and think, let's freeze that whole, okay. This is a container of water at 0 degrees centigrade. It's Friday and you were disappointed. You were hoping for some. Anyway, 0 degrees centigrade, it's water. I want to calculate what it would mean for 1 gram of water at 0 degrees centigrade to suddenly be 1 gram of ice. A spontaneous ice cube. It's easier to do with 1 gram. Okay. I can do this calculation because most of you know that it takes, I hate these numbers, 80 calories of heat energy could be removed from 1 gram of water to make, sorry, would have to be removed from, from 1 gram of water to make it 1 gram of ice, or vice versa. You'd have to add 80 calories per gram of heat energy to melt 1 gram of water. So if I take this delta Q of 80 calories for 1 gram, and I use this formula, I put 80 in here, and I convert it to the right units, I won't bore you, and I use 0 degrees centigrade, which is 273 degrees Kelvin, and I use Boltzmann's constant, which is exceedingly small, 1.38 times 10 to the minus 16 in CGS units. I mean, most of the people, when you say that, think you belong to the 6th century BC. I mean, this is not SI units. These are real physics units. The bridge will fall down, but the water will spontaneously nucleate. You're not going to give me a job, huh? Okay. This is 80 calories. I'm going to convert that to joules by 4.19, and then I'm going to make 10 times 10 to the 7th to convert it to ergs, and then I'm going to have this in the right units. That's already in the erg units, and I'm going to put in 273 degree Kelvin, and I'm going to work out the back of this. I'm going to work it backwards. I'm going to say, thanks to Boltzmann, this is what happens molecularly, this is what happens thermodynamically, bulk-wise. You measure it with your little calorimeters. The relative probability that I have 1 gram of ice in my container relative to no grams of ice, that the water all stays at 0 degrees centigrade is probability 1, and probability W2 is that I have all the grams minus 1 are water at 0 degrees centigrade, and 1 gram has spontaneously become ice. When you're dying, you yell a lot, you know? They can't sleep on you. Okay. Delta S12 over K, and if I work that out, that's equal to delta Q1 on 2 on KT. I won't do the numbers, but notice what happens now. Delta Q12 is negative because I want to convert 1 gram of water to 1 gram of ice, so it has to have 80 calories transferred from the water to the rest of the water. So it's going to be negative. Negative with a mod sign. And if you work the numbers out, and I did, it's e to the 2.3 times 10 to the 22. The probability that 1 gram of water will spontaneously nucleate out of, it doesn't matter how much other water I had, I only need 1 gram. By the way, I need a large lot of water. Can anyone tell me why I need a lot of water? Because I'm sweating a lot and thirsty. Okay. I need a lot of water because I don't want the temperature to change. I want to take 1 gram, I want to take 80 calories from the water, okay, and convert it. I want to take 80 calories from 1 gram of water and make it into ice, but the 80 calories has to go somewhere. This cold water. So it's going to go to the rest of the water and heat it up a bit. But if I have a huge amount of water, you know, huge amount of water, then this thing won't change very much. I'll still be like a constant isothermal temperature bath. Well, that's not very probable. But if I do it the other way, I add 1 gram of ice at 0 degrees centigrade to this container of water at 0 degrees centigrade, then I'll take 80 calories from the water and transfer the ice. The ice will gain 80 calories. There'll be a plus sign here. And the probability of that is e to the 10 to the 23rd. So you can feel happy if you put an ice cube in water, it'll melt. You know, 6 o'clock this morning, you know, I shoveled 430 tons of effluent in the backyard. I drove 43 kids. I swam a mile. I watched Australia win 89,000 more gold medals. I argued with my family. I didn't have a drink. And some yo-yo lecturer who's been here for 31 years tells me that if I put a gram of water in a container of water, it'll melt. We're really glad you came. And some of you will probably have a parking ticket for it as well. It's just really not what it is. But what I want to tell you is that what Boltzmann is telling us is that what's happening macroscopically is related to probability. Just like what happens with the distribution of the molecules in the room half and half. That the reason certain events occur, by the way, it doesn't happen irreversibly. That is to say, this is what I want to tell you. This is back to the arrow of time. If I start out with 1 gram of ice and I let it melt, which is heavily probable, in the water, I don't find after a period of time that it happens back again, that 1 gram of water will spontaneously nucleate or condense into 1 gram of ice again. I will find it happen, but it will happen with a probability of e to the minus 2.3 times 10 to the 22. So things can happen. You may live forever, and I hope you do. And I hope the last voice you hear is mine. But the probability of that happening, mind you, most of you now are indoctrinated. You'll hear it forever anyway. Old students, I was in a tram about 1.5 years ago going to the city, and one person moved towards me like they were going to drop me. And this person came to me, and the girl, rather attractive, and I thought, like, she's really interested in me. And she said, I'm not. And I said, why? She said, I took first year physics with you in 1903, and I still wake up in the morning hearing that. So you don't have to live forever. You're all messed up now. So probabilities, that the arrow of time, so Boltzmann started to say, why is this so? He did this for us. He linked everything microscopically for us. He's the one responsible for linking the probabilities that events occur with the thermodynamic results that you see in the laboratory. So he's saying that the reason things occur is because, and you might say, well, that's surprising, but we can now really work with that because there is a relative probability for it, and we can relate these probabilities to real physical quantities like heat energy transfer and temperature. We owe him this. This is one of his greatest results. Essentially laying down the molecular foundation for why physical processes go in a particular direction in time. Why there's a certain flow or unidirectionality in the way processes go. They can go the other way, just don't wait around for it. Give you an idea of how big these numbers are because I saw it on the television last night. I love it. There's 3 times, I'll put it in my language, there's about 3 times 10 to the 7 seconds in a year. If you do 60 seconds in a minute, 60 minutes an hour, well, I won't bore you with that. Already wasted a lot of the lecture. 3 times 10 to the 7 seconds in a year. So suppose you count that number. 1, 2, 3, 4, a number a second. You can do much better than that. You're going to waste your whole life when I'm finished with you. You're going to go 1, 2, 3, a number a second. It'll take you 1 year to count 30 million. So suppose you wanted to count a billion. A billion. I love this because it's related to something I heard on the television. Suppose you want to count a billion. And I won't make you count a number every hour of every day, 7 days a week, because you might eat, you might sleep. You shouldn't reproduce if you're doing things like that. Because it could be genetic, and you'll have a whole lot of people in the world sitting at 1, 2. Okay. Certainly not going to be good for the gross national product. Okay. So if you take 3 times 10 to the 7 seconds, and you say I only do 8 hours a day, and I only do it for 5 days a week, you'll find the count to a billion takes about 101 years. And assuming you're going to start counting when you're about 10, you've got to live to be 111. I like this because I heard on the television last night that they were trying to explain to people how much money $1 billion is. When I know what $8.90 is, I know what 109 is at the telephone bill. Maybe Tony will give you some of that for messing your lives up. But $1 billion, who can think in terms of $1 billion? But J. Paul Getty, the great billionaire in America, said to some very wealthy millionaire who was dying, who was rather showing off, he said, if you can count all the money you have, count every dollar you have, you ain't got $1 billion. Now, he didn't know anything about probability. He knew a hell of a lot about money. I know a lot about probability. I don't know a damn thing about money, but I do know that if you try to count $1 billion, which is how much money he had at the time, a few billion, take you 101 years. So if you try to count these sort of numbers, it's just not going to happen. I'm trying to give you the feeling that these probabilities, if I do it better, go like e to the minus the number of molecules in the container. If I'd been a little bit more theoretical with you and a little bit less lay-like, I was told that you're lay people. I don't know what that means, but I won't tell you what I thought. Anyway, I just said I wasn't supposed to do anything, but maybe we can talk afterward. Anyway, if I was a little bit more clever with the formulas and not the numbers, I could tell you that this number here is actually the number of molecules that turn out to be in 1 gram of water. And that the probability that this thing occurred, the relative probability that 1 gram of water became 1 gram of ice, goes like e to the minus the number of particles there are in the new state. And that's humongous. And that's due to Boltzmann also, that these things go like the number of molecules, like by 2 to the 10. Okay, that's really beautiful. And plus the other way. Okay. So what this gives rise to, if we're really clever, is the mechanics. Boltzmann took these relative concepts of probability and turned them into what we now call statistical mechanics. That is to say, if you have something like 6 times 10 to the 23rd particles, the last thing in the world you want to do is write F equals ma equations for them. I've already told you that a billion is something you can't imagine in your lifetime. Well, I shouldn't say that. Some of you may make 111 years assuming you started counting to 10. You start now, looking at the age of most of you, it'll be considerably longer than 111 years. Okay. So if you're going to play with 6 times 10 to the 23rd, you're not going to take all those lovely lectures that you've had before, F equals ma. Imagine this. You got a glass of beer. You're going to write down the equations of motion for 6 times 10 to the 23rd molecules. M, d squared, x, dt squared. And you're going to take one molecule, and you're going to have force on it from 6 times 10 to the 23rd molecules minus 1. And then you're going to do that for the y and z component of molecule 1. And then you're going to write all those equations down. And then you're going to solve them. You're going to solve 6 times 10 to the 23rd cup as long as your differential equation. You can't even count to a billion in your lifetime before it's silly. You're going to do that. And what's more, to solve them, you've got to know the initial conditions. To solve these differential equations, you're going to know what, imagine going to a bar and some of the people I drink will say, I wonder what the position of the molecule is. I'm not going to get that position of that molecule. I only know where it is. It's going to be somewhere between my eye and my face. They're going to look at me like, bloody yank. What do you hear when they say yank go home? Okay. I've got to know the initial condition, the velocities and the positions of every molecule. And then even if I knew that, what would I have? I'd have a printout the size of the cosmos 40 billion times over again of what every molecule is doing. So in order to know whether ice melted or whether water nucleated, a gram of ice came out, I would sit there with these humongous pieces of numbers trying to figure out, well, I got a gram of ice. It's hopeless. You can understand why he used the chair. You can't understand why he waited until he was 61. I would have drank all those bloody molecules. Okay, but I wasn't Boltzmann. And so Boltzmann started to apply the concept of probability and statistical ideas. I don't mean like actuary stuff about how long you're going to live. I mean real probability theory from mathematics to the dynamical laws of nature, mechanics, in order to find out what happens on the average. So you never have to know what any one molecule did. And from these concepts that I've been talking to you about here, what's probable and improbable, he developed a deep microscopic understanding of mechanics statistically for explaining how you take large ensembles of molecules and find what their configurations are going to be. As a result of this, he found, just to summarize a little bit, he found that if you start out with a system at some time t that is not in equilibrium, some parts of the gas, say it's a box of gas, some parts of that gas are hotter than other parts. Some parts are denser. You start out at some temperature T, the system is not in equilibrium. He found that as T went to infinity, or as T evolved along, let's not say infinity, to a very long time, this system developed its equilibrium configuration. Its equilibrium configurations were the kind of things I've talked to you about here. Suppose you started out with half the molecules in one side and none in the other. How long would it take until you had an even number in both sides? What would happen if you were changing the temperature? And over again, he found by applying his statistical concept that the system would reach an equilibrium configuration, and that's what I've been doing for you now, applying equilibrium statistical mechanics, such that the systems would have the kind of probabilities that I've talked to you about very loosely now. And that it was almost impossible for the T, it was almost impossible as time kept going on for the systems to reverse themselves. That is to say, that as the system approached equilibrium, it always approached equilibrium by way of chaos or randomness, the kind of things we've talked about now. Once you apply statistical mechanics, it's not random to begin with, but once you apply statistical concepts to your mechanics, you've made your answers randomized. It's called molecular chaos. You put in random concepts in there. And so no wonder as T went to infinity, and he knew that. As he reached equilibrium, he reached the kind of configurations we've talked about here. But nothing went backwards. That is to say, if you wait a long time, you're not going to find that the opposite things happen. You're not going to de-age. You're not going to find some time goes on and then you get younger. You're not going to find that the this ice goes in the other direction. You will find it with a probability, so it can happen. It's essentially not going to happen at all. So there's an arrow of time. Why did that bother him? Well, what really bothered him, let's take a look at, do you know mass times acceleration is force, and force is length per time squared, huh? Time derivative of velocity. It's got the dimensions of light, feet per second squared, something like that. Look what happens in the original mechanics. If you take time, this is what physicists like to do, this is time, length on time squared. You take time and make the equations reversible. You do that. You take t and call it minus t. Because in the acceleration, the time appears squared. If you take time and invert it, assume it has a symmetry, that you can go backwards as easily as you can go forward, Newton's equations give you the same answer, that you can go backwards as easily as you can forward. The equations are what is said to be invariant under time reversal, that if you take time and change it to minus time, the equations are invariant. So here's the Boltzmann starting out with the mechanics of Newton, which is perfectly time reversible, applying statistical concepts and finding out that you can't get it reversed. But that's you doing that. You're applying the statistical concepts. So why can't things reverse? Well, in 1901, a French mathematician and physicist known as Henri Poincaré proved that every one of these systems, of course, would return to whatever initial configuration there was. So again, we're in a little bit of sweat. I got to relieve for a while. I had half the molecule, all here and none here, got them all homogeneized, and now Poincaré said, in some period of time, they're all going to be, you're warming up, all over here. You guys, I was with you to begin with, but you let me down. All of them are on the other side, but Poincaré found that the time it took to do that was something like e to n. That's what Boltzmann found, the total number of particles in your system. So these systems will return dynamically, or they'll return statistically for different reasons, but essentially there's an arrow of time that is so long, humongously. Think of this, e to the 10 to the 23rd is not the kind of time you want to worry about. People say, what if you do it to powers of 10? Oh, we'll do it to powers of 10. There's hardly any difference between 10 to the 10 to the 23rd and either the 10 to the 23rd. There's a 2.3. Who the hell cares about a 2.3 when you've got 10 to the 23rd to get over? You're not going to wait for that. You couldn't even count to a lousy billion in your lifetime. You're going to go to e to the 10 to the 23rd seconds. So I'll come in a second. I'm winding down. If you wait a long time, says Poincaré, all these dynamical systems will return to their initial configuration. This e to the n is intimately connected with the probabilities that are built into to Boltzmann's kind of thinking. Okay. Well, I want to tell you in the last 5 minutes that the arrow of time, so I can put up some buzzwords, this arrow of time, or the unit of eventuality, in physical case is really related to the flow, people like to call it the flow of entropy, which simply means that systems like to find their most probable configuration. They want to make entropy as big as possible. They want to find their largest configuration probability, and the largest probability for configuration is overwhelmingly the configuration that's random. I tried to show you that to begin with. It's a random configuration where there's an equal number and 10 and 1 is not random. 10 and 0. You have 10 on one side and 0 on the other. You have a really ordered configuration. But if you have 5 and 5, or worse than that, n on 2 and n on 2, you have a very random configuration. You don't know which n on 2 is here, which n on 2 is here. You just know there's n on 2 on one side and n on 2 on the other. You've got n on one side and 0 on the other. That's a really ordered state. So systems want to be disordered. They want to be chaotic. They want to be randomized as they approach in equilibrium. They want to have large entropies. These concepts are due to Boltzmann. They start out thermodynamically with Carnot and Clausius, and they're formulated by Boltzmann. I've only given you a rather lay-like, sounds like some lay-like, are you all young enough? He was one of Boltzmann, no. I would love to know that Bob Dylan was a teacher who Boltzmann, in his deep recesses of smoking and messing around, that he reads statistical mechanics, but it's probably not true. I told him I listened to all his songs, he was equally disinterested, but he wasn't there. Okay. C.P. Snow once told a congregation of people in Trinity College in Cambridge when he was talking a little bit about, did anybody understand what this is involved with the second law of thermodynamics? Did anyone understand entropy and the flow of processes in nature and arrow of time? They all looked at him in a real disdainful way. He was very disdainfully back and said that not to know the second law of thermodynamics, or not to know what entropy was, or not to have a loose idea why configurations in nature are the way they are, is like to have no knowledge of music, or to have no knowledge of literature, or not to know any Shakespearean sonnet. Well, I don't know how true that is. I don't know one Shakespearean sonnet, but I know a lot about entropy. But I think his point was very good, that these are the concepts that really control the physical world, and they belong to our culture in the same way that music, Bob Dylan, or Beethoven belong to it. All right, enough of that. I don't have any books of culture studies, so I don't stop. Okay, so I'm going to call him the father of statistical mechanics. And because of him, we now know all sorts of exotic things. And, you know, if I was selling this in Canberra, I have a spin glass and a semiconductor, and I look at my colleagues out there who are making an incredible amount of grant applications based on something that would glow in the dark and lift balls and thousands. And I hope they do that. Get this out of this fund. And I get more money for teaching these things and do this. No, beautiful sort of stuff. But it doesn't go that way. But all the kind of development in modern understanding of what happens at the molecular level really followed from Boltzmann's knowledge and insights about how to make things statistical, how to learn about probability, and how to learn about the arrow of time associated with the flow of entropy. I started that, didn't I? I don't know where I did that. I started to talk about time's arrow and the flow of entropy and probability. This is wanting to be, and this isn't going to surprise anybody when I tell my wife that nature wants to keep configurations that were as chaotic as possible. She just points to my socks or the sofa, or that I sleep with the dog or something like that. She makes, anyway, time, flow of entropy, or that there is probability wants to be maximized. But that's just the tip of things I've shown you, and I really wish I had a course. I see some of the people who just had nervous breakdowns and have survived my course would go into 30 or 40 lectures of this, and the stuff is really deeply beautiful at the fundamental nature, at the fundamental molecular nature. And so he's the father of statistical mechanics, and flowing from him were J. Willard Gibbs, maybe some of you have heard of J. Willard Gibbs, and then Al came along, and he put the final touches on the ideas that were started here. So after Boltzmann used to be a great opera lover. Let's have a little Boltzmannology. Boltzmann used to be a great, it was a great lover of opera. Used to be, no lie. And he used to go to opera carrying a large green notebook, beautiful vellum notebook. Go to all three, you can see his original notebook. And he would sit and jot things down when he was in the carriages going, or even when the intermission in his life, and even during some of the operas. A very famous socialite in San Francisco invited Boltzmann to there in 1900, a year or so before he died. He paid his whole way over, and he had one wonderful time going to the San Francisco Opera. She fell in love with it. She had read these papers, or she'd read the popularization of them, and she saw the arrow of time and the flow of entropy and probability as major insights into one's cultural understanding of the world. Anyway, Boltzmann had a wonderful time, and then went home and hung himself. So when I told my wife back, she said, well, we're either not going to America, or we're not going to San Francisco. I don't think I'm being silly, I don't think he hung himself because he went to America. I'm going to come to Australia, reversible process, I think, but when my arrow of time, and he's trying, I'm never going to get back, and I haven't studied. He got very depressed. What really worried him, why he got depressed, was he could see that the original equations he played with were time reversible, but none of his physics were. So there was an arrow of time that emerged from his statistical mechanics that were not intrinsic in the original equations that he started with, individual Newton's equations. And we still don't have a complete idea of the arrow of time. We don't understand more than the kind of concepts I've given you now. Well, if I had a little bit more time, and I don't, so I'm going to end up in a minute. Time has entered into quantum mechanics. In fact, time's uncertain now, as you know. Uncertain, you know, quantum mechanics, the conservation of energy doesn't even really hold. So on very short conservation of energy on molecular or atomic or subatomic processes. You can have energy uncertain by an amount times the uncertainty in time is that energy is uncertain equals a Planck's constant. And so time is not only certain, it's uncertain. And energy is not only conserved, it's not conserved, but the violation of energy is conservation is related to the uncertainty in the time interval over which that happens. So quantum mechanics has made it even more uncertain about time. And then we have cosmology. Obviously time is very important in cosmology, like there's some, if you believe the modern paradigm. My wife told me to use that word. We're all educated people, even if I was Lucy used, we're all paradigms. I'm a dollar man myself, but some of you are paradigm, and you would know the word paradigm. I don't, because you use it in a word too. Okay, here. Okay, suppose there is this thing called the Big Bang, and if there is, time starts in some equal zero, and we're supposed to believe that before that, the question of what there was doesn't even make any sense. That there wasn't anything called time or space. Now, what was before that, it doesn't even exist. The question itself doesn't make any sense. Is that sensible? I don't know. But the predictions of it have some reality about them. And then as things emerge and the Big Bang blows up and we get a whole universe, is it going to return backwards? And if it returns backwards, is that an arrow of time? The great English astrophysicist and relativist Roger Penrose believes that it is. There's some intrinsic idea of an arrow of time that involves quantum mechanics and gravity in a kind of quantum gravity area. And we'll never really understand the deeper meaning of the meaning here. Everything has a deeper meaning. And, we never know there's another layer and another layer. That somehow it doesn't have to come back. It may be an ever-expanding universe. But if it should come back, and he thinks it will come back by going through a series of black hole explosions which will reverse it, but I won't bore you or entertain you with that. I'd love to go on. I don't know if you're up to in your lifetime more than one of these, but my wife thinks we should all get medals and pay for something. Okay. If there is a return, if the expansion is such that it's arrested and comes back, and there's enough mass or energy density to return it, then the whole universe will return. Does that mean that there is an arrow of time? That everything that did occur this way is going to occur backwards? And is that arrow of time related to the singularity at the Big Bang, where of course, if we really understand what's going on, we need quantum mechanics and general relativity, so is there going to be a quantum general relativistic arrow of time that gives a deeper and more meaningful meaning to these things that Boltzmann hung himself for? I don't know. These are the kind of questions that people are asking. Well, I have to tell you that I like poetry, but I don't understand physics, but I like it. I keep thinking if I talk about it a lot, I might figure it out. And there's a poem I like a lot. Everyone has a poem. You look up time in an anthology of poetry, you'll find the words time and space overwhelming in here. Poets are all about that. They talk about time expanding. They talk about things being chaotic. Poets understand about the world. They just don't talk about entropy and time and cosmology and what have you. But my favorite poet is Wallace Stevens, because I don't understand the damn words he writes. You got to like things you don't know about. Understand things. It's boring. I'm going to stay with my wife because I don't understand it. She's completely understands it. It's an arrow of time. He writes the poem. He was an insurance salesman in Chicago, and he wrote poetry on the side. But unlike one of these things he was discovered after death to have thousands of them, he published them and made lots more money doing this than as an insurance salesman. And he's listed as the greatest lyrical poet since Emily Dickinson. He was all kinds of Emily Dickinson. I think I understand her. Some lady told me I was in real trouble, but you can't understand her. Anyway, he wrote it. It's just amazing. It's about time, but he entitled the poem The Pure Good of Theory. And he deduces that there's no damn pure good of any theory at all, which I hope you won't be left with. But to him, time is a horse that runs in the heart. A horse without a rider on a road at night. The mind sits listening and hears his past. Well, I've done that on many nights, and I can hear my arrow of time coming rapidly to an end because I have no more time. I work for Reading's bookstore in Ligon Street. But if you'd like to peruse these or copy down some titles, these are lovely books. This one here, I'll just hold Tony for 1 second. This one came out last year. It is on Boltzmann and the Arrow of Time and discusses all of these themes, including chaos, the famous buzzwords, biological clocks, chemical reactions. It's a lovely book. It's called The Arrow of Time. And I'll leave them here. And I should have made a list of them and handed them out, I promise. And then, you don't want all of these. There was an Englishman called J.W. Dunn. Anyone ever heard of him? It's wonderful. You can't get this book anymore. And he was a psychologist. And he would wake up in the middle of the night after learning about special relativity and try to plot his dreams in four-dimensional space-time and found some incredible results as only wildly eccentric English people can. It's heralded as a classic now. I bought it for 50 cents in England. Well, actually a couple of fees, but the guy who wanted to sell it needed a drink, and then I found out it's important. But if you want to know about Einstein, Einstein was involved with statistical mechanics. A beautiful paperback by Jeremy Bernstein called Einstein. The most readable. Everyone has a book on Einstein that's most readable. This is really beautiful. Cosmology, the search for the edge of time, black holes, and the kind of stuff I've talked to you about before here. In Search of the Big Bang is all about time. Chaos is all about what happens if you start away from equilibrium and what happens as chaos is approached, what happens then. And there's other types of chaos that come. There's stuff called bifurcations that you might have heard of, and chaotic theory, which is intimately related to things that Boltzmann had his nose on. So there's hundreds of books, but if you want a book that best epitomizes the stuff that I told you here and will make it all clear to you, and you didn't waste the time, it's called The Arrow of Time, and I'll write the author's up. It's really beautiful, and I get I get 35 cents for every dollar. I just give you this. It's really a great book. It's not just great because I said it's been reviewed good. You know, it's top of the Times bestseller. Somebody who didn't understand it said, I didn't understand it, but I believe when I do, it will be the most important book I've read. By Coventry. Steve Coventry. It's a beautiful book. It really is. And Roger Highland, sorry. The publisher is Flamingo. And all the bookstores involved in it around town have it. Also, if you walk in, it's selling better than Bob Hawke's. I don't know if that's a lower bound to its worth. Okay, you can look at these, but that's a really beautiful book. If you got $14.95. It is. I saw the man is going to take his clothes off for me if I answer this question. I don't know what if you believe in the quantum electrodynamics as we think we understand it. We would apply quantum theory to it, and we would use the most inventive ideas to say, if you've heard of Feynman, you would have heard of. There's a great book. Did you read his biography by Gleek? There's a great Nobel Prize winner who's now dead. He didn't hang himself beside his stomach cancer. Richard Philip Feynman. And there's a beautiful book called Genius. And the author is Gleek. He wrote a well-known book on chaos. It's a paperback, and it's a biography of this great physicist. Feynman would tell you that in order to know how anything occurs in nature, you should write down the process going from some point to some point as an integral over all possible paths. And he would say yes. He would say that the history of the electron would be involved, that is to say what it's doing, would be involved with, and it goes like an exponential. It's a much hairier object. I want to leave you with a feeling that in your lifetime it's much too hard for you to possibly comprehend. Smart ass. I have to be smart ass. It's really hard stuff, but it takes a few to understand. It takes some force like some
huge period of time. But the return will be lost, or the probability of finding a return will be so big that you won't have it, but it's really there. So what Boltzmann would say is, on the time scale of the physical processes, relaxation of the gas to equilibrium, how long it takes when I actually take that system from state 1 to state 2, I don't care about the arrow of time. I mean, I care about it in the sense that my systems are trying to find large systems on relatively short periods of time, that is to say thousands of years even, want to find configurations which are random, most probable, which have an arrow of time. That works. The end result being chaos gives us the right answer. But over a huge period of time, say, I tried to indicate with Poincare, these fixed systems would come back, not one electron. These fixed systems would all come back to their initial configuration. And what worried Boltzmann was that he knew what he had done. He put in this idea of chaos, this statistical principle, randomness, so he got the right answer, or it turns out it's the right answer. But he worried, what does that mean about time reversal? He knew he lost it. He knew why he lost it. And he was desperately concerned to reconcile these 2 points. I would say that except for this cosmological problem about what happens to the whole universe in time, it has been resolved. That there isn't really a mystery about the arrow of time in a sort of locally happy. I want to leave you sort of content that on a local scale, thousands of years, the lifetime of the universe, 10 billion, 15 billion years, what does that say? E to the 10 to the 23rd second, or years. That everything is approaching randomness or highest probability configuration, and he was right to say that while we can't solve the exact equation, if we randomize it, we'll get the correct answer on very long periods of time, and we forcibly remove the time asymmetry. We put in an asymmetry by putting in the statistical or randomizing concept, because there are things we do to make these calculations. Well, Poincare said, essentially, don't worry about it. Even if you don't do that, these dynamical systems won't reappear in times which are other than even the end. So if you're using one particle, you're in trouble for all this stuff. And that's why on the 1 electron level or the 2 electron level, microscopically, all these mysteries are important. But when you're using a large number of particles in a beaker of water, or you're designing a chemical engineering factory, or you want to know about heat transfer, things like that, or why things get colder. Now let's see why the cold body got colder, hotter. So you put the cold body next to the hot body, and it worked out for you. It's much more probable for the ice to melt in the water. That's the cold getting hotter than the other way around. But of course, it will eventually come back to those other configurations, and I need even a statistical. But what good is it? I can't solve those original equations, and Boltzmann should have been relieved to find that even if he could, this is called the Poincare recurrence time. The time for the original equations that you didn't smear around with. The return is e to the 10 to the 23rd. You'll just never be concerned about it.
Okay, let's have another question. Yeah.
Does that help you in any way? So we put it in.
I think you probably answered it, but it's just my life coming on. I suppose I'm not blind. Time doesn't exist. So there's no flow of time in that sort of instant.
Why does it come? But if I make a measurement, the trouble with quantum mechanics is that that's fine, except that I don't know anything in quantum mechanics unless I start to make a measurement. That's about it. Photons can be doing anything, can be anywhere, as you say. Same with electrons. It doesn't have to be a photon. But I don't know anything about my system until I start to make a measurement on the system. That's the trouble with quantum mechanics. It tells you what you know anyway, because you don't know what it's talking unless you look at it. But in the microscopic world, it makes no sense to say that until I actually say what happens when I make a measurement. So I actually look at that photon, or I look at an electron with another photon. It doesn't have to be a photon. The moment I do that, then I will be making special types of states. I will be observing these things over certain intervals of time and momentum and position, which are uncertain, but I will have certain predictions about them, statistical predictions. Quantum mechanics is a statistical theory, but again, a different type of one that tells me statistically where that particle is within a certain range of, there's, I don't know what the formula does, but that'll be, there's uncertainties in positions and momentum. There's uncertainty there. So if I start to make a measurement, and I look at you with my eyeball, I bounce a photon. Well, I don't know where you are until I look at you. Say, gee, that's great. Physics is really great. I mean, you don't know anything until you look at it. I mean, physicists discover that. They pay a lot of money for that. But when I start to look at you, whether you're a photon, wherever you are, electron, I will start to localize you. The process of making measurements involves bounce
Bang, at a time interval of about 300,000 years, the radiation, would be quite right, the photons, the electromagnetic radiation, decoupled from all the matter within the universe. That is to say, the Big Bang, everything's a big fireball, okay? You believe the theory. As this fireball expands, it cools. Again, you can apply these thermodynamic rules and apply Wag's rules. And in around 3,000 years, the particles have cooled down so much that the protons and the electrons have formed, well, they've already done earlier than that, but there's already hydrogen atoms or molecules, and in 3,000 years or so, the radiation decouples from that. So the photons in the universe, the radiation is going its merry way. It decouples completely from that, and the rest of these objects have organized themselves into stars and galaxies and blown up, and spit out a lot of heavy elements of which we eventually got made of, like some process that made the Earth and the Sun, which I'd love to go into with the cosmology. But we are actually becoming a if you like, we're either having a heat death or freezing to death. I mean, our universe is becoming more and more pushed to states of higher probability, states of greater disorganization, to more and more chaos. So some people argue that eventually we will wind up as the 3-degree black body radiation, but we haven't actually become that heat death yet, if I can call it like that. The photons have gone their merry way, and it took, by the way, you don't want to be too glib about this. You can subtract 300,000 years from 10 billion or 15 billion, you still have 15 billion. It took 15 billion years for us to get here, to be thermodynamic the way we are now. But if the universe keeps on merging and expanding and more chaotic, then we will either, depending on the final scenario of the Big Bang, we will either merge with this cold back body radiation, which will be getting colder, or we'll have a crunch which will take us back. But at present, we're not related to that. With the photons, the photons linked off on their own way and decoupled from. We're just sitting in that gas, but we're not connected to them. There's nothing photons can do for us. You think about what they can. I don't know if I'm answering your question, but we took 10, 15 million years before we were even made. So it's taken that long to make the stars and the galaxies. I don't mean people. It took, the Earth is only 4.5 billion years old, but 15 billion years, it took 10 billion years even to get to the solar system. Then, I don't know what kind of biologist or creationist we are, each of us, but, it took a long time for life to occur. So, it's taking a long time for these processes to occur.
So you mean...
We are running down, if you like.
Norm, do you mean we'll get there yet?
We will get cold.
Can I get you back to Boltzmann?
We are approaching a cold, disorganized heat death, but we're nothing to do with the photons. They form off, they decouple. When a photon can't do anything to you, it can't do anything to a hydrogen atom other than bounce off of it, because the photons are too cold to fight the electrons in it or to ionize it or anything. So it's just a kind of fast 3-degree photon radiation, but it's not doing anything to the matter. It can't excite it in any way. But we are doing things to ourselves. We are becoming more and more disorganized. We are, the whole cosmos, right? These fireballs are much more organized state than all the chaotic galaxies and Earths and planets and everything. It's a big hot fireball. Now we're all in this chaotic state. So we are getting there. We will, if one of the endpoints is correct, wind up no better off than this cold background radiation, which is harmless to the present, but will be like it. If this heat death, those probable states are more chaotic and disorganized ourselves. By the way, chaos means disorganization. Nothing could be more disorganized than a random distribution of molecules. Nothing could be more organized all in one container, none in all in one half, and none in the other. So we are disorganizing ourselves. Not personally, not politically, but physically. about 3,000 degrees Kelvin. I mean, you can argue some say 4.5, some say 2.9, about 3,000 degrees. Yeah. And then the protons and the electrons are allowed to come together and make hydrogen because the photons are not energetic enough to ionize. And you know you have to have you need the photon hot enough, energetic enough, high enough frequency, hot enough to be able to ionize. And so in 300,000 years, the radiation and matter are in equilibrium at about 3,000 degrees Kelvin, but that's roughly the temperature in which what is called called the era of recombination. The protons and the electrons can combine, and the photons are not energetic enough to ionize them. And so the photons just form this background C, and then you do have large clouds of hydrogen. I don't know that anyone knows whether they were uniform or not. There must have been some density fluctuation in those clouds because there has to be little clumping that went on. So where were the pockets of a little extra mass for nucleation? So there were some form of uniformity, but there was some irregularity in there, some density variation somewhere. It couldn't have been totally uniform. There were some density fluctuations which acted like gravitational wells, and mass was pulled in. That's the general theory. And clumping began, and clumping begets clumping begets clumping. I spent the Bible like that. And then these local things happen. That's the kind of picture. Am I answering your question? Yeah. So there's hydrogen gas at 3,000 degrees centigrade, but it can't be totally uniform. It must have some ripples on it. And that's what they think they see when they look at if you've seen all this stuff in the papers about the 3-degree light body radiation has anisotropy to it. That's to say it looks different, you look in different directions. And that's the ripples that must have been around, slight unevennesses in your hydrogen cloud for little lumps to start to nucleate from them.
Yeah, the thing is, right, that's all different.
So it's not uniform. I'm saying that whoever told you it was uniform,
Maybe the slight
well, it's uniform, but that's a teeny bit of non-uniformity. But that's how we're here.
Hey, Norm, I want to ask you a
I
question.
don't want to stop him. I'm just going to drink.
No, he's had his go. I want to ask a question. Come and take one of his courses. He gives it every year.
Or buy a book.
Norm, you gave us the impression that Boltzmann got terribly depressed because he was losing arguments with himself.
That's right.
I was under the impression that he kind of got terribly depressed because he was losing arguments with his contemporaries, none of whom believed in the reality of atoms and molecules. Now,
That's right. I did it in a slightly dishonest way because I believe in the rogue elephant. Nothing is really done collectively. I mean, a lot of people think that work is done by building on other people. I like to think that it would all be important, but I'm not important, and if I'm not important, none of you. Sorry. I mean, it just seems like great advances occur from various people. So Tony is right that when Boltzmann was doing a lot of this stuff, he was worried about this problem himself. He writes himself that this most depresses him. But he was a professor of physics at a famous university in Europe, so he's not some crank who's writing really, but his colleagues don't believe it. They don't find all this stuff digestible. I mean, it's very subtle concepts. I mean, I'm looking at 6 or 7 people that have taken my course about 3 or 4 years in a row in 1993. And they're still finding it unacceptable. So, but that also depressed me very heavily. That's very true. His colleagues didn't believe it. Now, just to add one little point that's Tony's good on, thank you for putting on beam. One of the problems they didn't believe, underneath all this, which is amazing, is that playing around with the configurations of molecules made any sense at all, because most of the people, at least 50% of the scientists in the latter part of the 19th century, did not believe in the molecular view of matter. Everybody. So I would like you, if you have time, the second most beautiful book to read is this little book by Jeremy Bernstein and Einstein. It was reviewed by the New York Times and the Ballarat Centurion and Morwell Gazette and the New Jersey Local Person. It's a beautiful book, but one whole chapter in there is fascinating to read. I don't know any other one that displays it. It's not fashionable. They'll just say Boltzmann had a lot of critics, most of which didn't believe in the muscle. Boltzmann is actually one of the first people to give a molecular, well, not the first, but one And his first opening remarks in this paragraph is to say that one of the things he wants to do, in my language, is put paid to all the criticism of the molecular basis of nature by studying in detail, using Boltzmann's ideas, the concept of Brownian motion. That's the Brownian motion would be to you in simple terms if there was someone smoking. Now, impossible to get an example of that because of all the right reasons. But if there was some smoke thing, without getting disturbing the flow, you watch the smoke particles diffusing in the atmosphere due to molecular bombardment of the molecules. And he studied the motion of those smoke particles, and they were first studied in colloidal suspensions by a chemist called Brown, so he wasn't looking at smoke. Einstein gave a complete theory of the motion of how particles move randomly as they diffuse under the agitation of molecular motion that Boltzmann believed in and following his concept. And he gave a complete mathematical description of that. In fact, people believe today that this paper here is probably is equal to this paper is equal to this, and he would have got the Nobel Prize had he only done that. When Einstein's paper was finished, and it was said by all physicists, there's absolutely no chemist, there was no doubt that nature at least can be formulated on a molecular basis, whether they're molecules or not. So as Boltzmann say in the latter part of the 19th century, even using molecules as your concept for randomizing or distributing was a heretical thing to do. But Tony is absolutely correct. That's absolutely correct. That he was upset with himself because he somehow got an arrow of time from reversible laws, and he was upset with his colleagues because they didn't like his concept and they didn't even believe in the molecules of the systems that there was a molecular basis of the systems he was talking about. So it's 100 years ago, 150 years ago he was born. He lived to 61 or 62. So 90 years ago, okay, 1905, 89 years ago, people start to say, all right, it's okay, you can tell your kids different molecules exist. 90 years is not a long time. There are people alive today that were alive then. My daughter thinks I was alive then.
So if you'd hung around just for a little
Boltzmann-
longer, he would have been completely
Einstein said that if he hung around to 1906, he would have had the Nobel Prize. And in his lifetime, Tony's quite right to say, he would have been knighted as father of statistical mechanics in his lifetime. We don't even in his late 60s. We got time.
Okay. Well, thank you very much indeed, Norm. I hope you all enjoyed that.
Thank you.
We have some notes here of previous lectures for sale, and there's tea and coffee outside.